include things like the amount of water stored in an ecosystem, the amount of carbon and nutrients, etc., in the ecosystem, the biomass in the ecosystem of plants or animals, and then some properties of the ecosystem in relation to how it responds to disturbance, like its resistance to disturbance or its resilience to disturbance. So kind of like the specs of nature. If nature was a machine, the properties of nature would be sort of the size and weight of the machine and its how much stuff it contains. And then the other aspect of ecosystem functions is what nature does. The processes of nature. And so that includes things like the production of organic matter through primary production, the production of animal life, which we call secondary production, the rates of decomposition and regeneration of nutrients through decomposition is also one of the processes that happens in nature. And there's a bunch of other sort of fluxes of energy and materials that happen within ecosystems that we can sort of quantify and include within this triangular system. Next slide. So a term that's very similar to and related to ecosystem functions is ecosystem services. And the only difference between ecosystem functions and ecosystem services is that ecosystem services are the ecosystem functions that specifically benefit humanity. So it's kind of like an anthropocentric take on ecosystem functions. Basically, we're only paying attention to the functions here now that benefit humans. And so I made this little Venn diagram, the circle within a circle there. And the ecosystem services are sort of a subset of the ecosystem functions. They're the ecosystem functions that are beneficial to humanity. So some examples of those are providing food and clean water, which we need to live, protecting our coastlines from erosion, regulating the climate so that it's livable for humans and we can grow our crops and things like that, processing our waste because humans make a lot of waste and it doesn't just disintegrate into nothingness automatically. And so there's a lot of things that nature does that benefit humanity and are illustrated by this diagram here. You know, a functioning planet equals happy, wealthy humans. Next slide, please. Because of this kind of recognition that nature does things that are beneficial to humans, there have been increasing efforts to quantify those services. And we call this ecosystem services valuation. Sometimes even dollar values are applied to the benefits that we get, for example, from a wetland habitat. You know, you can look up papers in the scientific literature that tell you the actual dollar value per acre of seagrass, for example. And it is nice to have those ecosystem services valuations when we're doing what a lot of us in this room do and contemplating the pros and cons of destroying, protecting, or restoring an ecosystem. You know, what are we going to lose? What are we going to gain? What do we want to make sure we don't lose that we're getting now? And so this ecosystem service evaluation, one click please, it's become a really trendy kind of thing, right? I use a quote from a movie that's maybe 20 years old now where, you know, ecosystem services are so hot right now. Everyone wants ecosystem services valuations. And so I jumped on this bandwagon too. Next slide, please. And the ecosystem that I wanted to look at the values of is Vallisneria americana or Vallisneria neotropicalis, depending on who you ask, beds in the Caloosahatchee Estuary. So Vallisneria is a freshwater aquatic plant that looks a lot like a marine seagrass. It looks like turtle grass, but it's really a freshwater plant that just gets into the estuary a little bit, where it's the low salinity oligohaline. Next slide, please. There used to be a lot of this plant in the oligohaline Caloosahatchee Estuary. As recently as the 1990s, there were thick beds of this plant that extended all the way down to the Cape Coral Bridges. And we know this from the famous Hafakern produced in the early 90s. But we also know from water management district monitoring and other monitoring of the Caloosahatchee Estuary that these extensive tape grass beds were lost in the early 2000s due to a series of, you need 2 clicks please, a series of salinity intrusion events. So where the freshwater flow to the estuary was not sufficient to prevent salt water from creeping up into the upper estuary and killing this freshwater dependent plant. So now we're in basically a flatline situation. There are little bitty traces of tape grass in the estuary now, but it's just nothing like it was prior to these big die-off events. Next slide, please. And to kind of emphasize how much things have changed, I'm including a map from some monitoring that I did for the EPA in 2020, where we did a really comprehensive resurvey of the submerged aquatic vegetation habitats in the Caloosahatchee Estuary to kind of compare with that Hoffaker map from the early 90s. And we found that things were quite different. Let's get a couple clicks. One of the things that was, oops, too many clicks. One of the things that is different is that the extent of Vallisneria, which once was throughout the upper estuary, is just really narrowed down to a few sort of remnant areas in the upper estuary. And there have also been some changes in seagrass habitats as well. But basically, we're really in kind of a bad situation now with respect to this plant in the estuary. It's just not like it used to be. And because of that, a lot of restoration practitioners like David Seeley over here and nonprofit organizations that support habitat restoration have been undertaking these really ambitious and noble restoration efforts in the estuary. The main technique is to plant Vallisneria in herbivore exclusion cages. One of the problems with restoring this plant, and it's a kind of common problem in plant restoration in a lot of places, is that once the plant is at a really low abundance, it's hard to bring it back because of things like herbivore pressure. And we think that there's kind of like a threshold of abundance that it has to reach before it can sustain itself. And so the theory is that if you give it a head start by protecting it from herbivores in these cages, then maybe once it gets going, it can get to that stage where it's sustaining itself again. And we get back to that kind of situation like we had in the 90s when we had a lot of the plant. The other thing, of course, that we need to do is not kill it again with a salinity intrusion event, but we've been working on that through hydrologic restoration projects like the C43 reservoir and changes in the Lake Okeechobee release schedule and things like that. So we're actually doing okay on that end. We haven't had so many really big salinity intrusion events in the upper estuary. But it's really not coming back on its own. So that's why we think we need to do restoration like this. All right, next slide, please. So restoration is expensive, and that's one of the reasons that we would really like to know what we stand to gain from bringing the plants back. And so different people have been looking at different aspects of the benefits of these of this plant Vallisneria in the estuary, and I'll just take down this list of some of the benefits that have been examined. One, and the reason that the Angular Action Foundation nonprofit organization is supporting the restoration is because there's a lot of evidence from other ecosystems, and we expect that it's true in this system as well, that restoring these underwater plants to submerged aquatic vegetation enhances fisheries productivity. So basically the plants support small epifaunal invertebrates, which are consumed by small fish, which are consumed by large fish like snook and tarpon. The plants are also food directly for charismatic megafauna like manatees, ducks like widgeons, waterfowl. So they provide food and habitat for wildlife that draws visitors and that are sort of appreciated and that benefit the economy by their presence. The plants also can stabilize the sediments. They can prevent resuspension events and improve the water clarity, and that we think is one of the ways that underwater plant communities kind of help sustain themselves by keeping the turbidity down. That can also have benefits for shoreline residents by reducing shoreline erosion, reducing the amount that sediments are moving around and the frequency with which dredging needs to be done. And then the ecosystem service benefits that I focused on in this study were related to the removal and storage of pollutants. I put a little asterisk by pollutants, because the kind of pollutants that I'm talking about are the pollutants that we call quantitative pollutants, which means that they're things that occur naturally in the environment, but become pollution when they're present in excessively large quantities. So nutrients, for example, are an essential thing for life, but they're a terrible type of pollutant in excess because they cause harmful algal blooms. Likewise, carbon is the building block of life, but excess carbon dioxide in the environment is a pollutant because it causes global warming and ocean acidification. So we'd like to get rid of the excess of carbon globally, and we'd like to get rid of the excess of nutrients locally. And this is what I tried to investigate in the next slide, please. So some of the ways that we think that underwater plants like seagrasses and Vallisneria, the seagrass, remove nutrients are directly by absorbing the dissolved nutrients through their blades. They can also absorb nutrients from sediment or water, and the nutrients then are no longer in the water where they can fuel algae blooms. They're locked away within the tissues of the plant. Furthermore, the plant leaves and roots that settle to the bottom and get buried in the sediment can store those nutrients underneath the ground away from the water column where they might stimulate algae blooms. So both the tissue storage of nutrients and the sediment storage of nutrients are important ways that we think these plants can get nutrients out of the danger zone in the water column where they might cause algae blooms. There's another process, denitrification, which is a bacterial mediated process that happens in the sediments, especially around plant roots. And that's another way that plant communities can help get rid of excess nitrogen, but we didn't quantify that in this study. That's something for the future. Next slide, please. So the goals of our effort at quantifying nutrient services here were to estimate the amount of carbon, nitrogen, phosphorus stored in the Vallisneria that's in the Caloosahatchee Estuary, and to find the rate of storage of these three materials, carbon, nitrogen, and phosphorus, in the sediments of the Vallisneria meadows in the estuary, and to do that estimation both for the amount of Vallisneria that there is right now, which is not very much, and for the amount that there could be if we restored it to 1990s levels, which is a lot. And because this is an estimation exercise, we also need to keep track of our uncertainty in this. So we try to incorporate that in our modeling exercise, include our level of uncertainty. Next slide, please.
I forwarded here. Let's see. There we go.
Okay, all right. So one of our initial steps, and really the thing that got us going on this, was a grant that Florida Gulf Coast University, where I work, received from the CHNEP. So this funded some mesocosm studies where we planted the mesocosm and field studies where we planted the plants, we altered nutrient conditions, and we looked at the absorption of nutrients from the environment into the tissues of the plant. We looked at stoichiometric ratios of carbon, nitrogen, phosphorus in the plants. And these two images here show the plants growing in mesocosms, and you can see that the water is tinted green in this mesocosm. That's one of the ones where we added excess nutrients to the mesocosm. My former graduate student, Brandon Krebs, worked really hard on this study and did a great job, but we had some regrets afterwards. You know, there were some artifacts of the way we set up the experiment that limited its realism, and we couldn't quite answer our whole question based on these mesocosm experiments and field studies alone. But they gave us some valuable ingredients that we could use in a modeling approach that let us get further along in our goal of estimating the value of these plants. So I want to talk about that now. So next slide, please. So some of the data that we got from those mesocosm and field experiments became ingredients in our modeling exercise. And we also had to add a lot of other ingredients that we got from other places to our effort to estimate the carbon, nitrogen, and phosphorus storage. So let's get one more click. So some of the other ingredients that we had to add were estimates of how much Vallisneria there is in the Caloosahatchee Estuary. So chute density data, number of chutes per meter squared. We also needed to know how big the chutes were. Some of the Vallisneria chutes in the estuary now are really puny, but in healthy environments, they're big. So you need to know how many chutes there are, how big each chute is. We need to know what the percent carbon is of a Vallisneria chute and the amount of nitrogen and phosphorus proportionally in the chutes as well. We need to know what the entire area of the estuary is that the Vallisneria is living in. And for the sediment sequestration estimates, we need to know rates per meter squared per year of deposition of carbon, nitrogen, and phosphorus. So next slide. I'm going to talk a little bit about how we kind of did the modeling and how we got data for each of those parameters. I just want to say that we didn't just make kind of one model estimate. We sort of ran the model for two scenarios. One with the current abundance of Vallisneria, so we had to get data on the current abundance, the current size, the current nutrient levels in Vallisneria, and a full restoration scenario with more Vallisneria. And so obviously in the full restoration scenario, our estimates of carbon, nitrogen, and phosphorus storage would be higher. Also within each scenario, we had three sub scenarios, one which was our best estimate, and then we also sort of bookended our estimate in sort of a low end and a high end boundary condition. Next slide, please. So the way that we got our estimate of the current abundance of Vallisneria was through direct measurements from these 100 shoreline perpendicular transect surveys that we did in 2020. So I know 2020 is not present anymore, but it's in the recent past. All right, so that's where we got our current abundance data, and it's not very abundant, 4.7 chutes per meter squared on average in the zone of the estuary that can potentially support Vallisneria. And then for our fully restored abundance, we looked at historical monitoring data from the same area, and we got the average figure of 257 chutes per meter squared, which of course is a lot more, and that's from 1998 and 1999. That's the average of monthly measurements from 24 months there. We use confidence intervals around that as well. Next slide, please. For the chute size, we had direct measurements of chute size from the field. So we plucked out one of those tiny little chutes, well, many of those tiny little chutes, and got their average weight in 2021 during a field experiment. And then we compared that to mean chute weights from monitoring in the late 90s that was reported in the literature. And chutes were much bigger than. Next slide, please. We got carbon fraction from direct measurements of the tissue stoichiometry in 2021. Next slide. And we got the carbon to nitrogen ratios and carbon to phosphorus ratios in a variety of ways. We used both field measurements. So basically we plucked, dried, and ground up the grass blades from the field now and analyzed the ratio of carbon, nitrogen, and phosphorus. But we also bounded those estimates based on the tissue stoichiometry ratios that we got when we grew the grass in really low nutrient conditions and really high nutrient conditions, so that we could sort of see sort of the full range based on the sort of stoichiometric plasticity of the plant. What possible nutrient ratios you could have in it. Next slide, please. For the habitable area estimate, we use the assumption that the grass is not going to grow deeper than 1 meter depth. And then we got a bathymetry layer for the estuary from the South Dakota Water Management District. And for the part of the estuary upstream of the Interstate 75 bridge, we didn't have a comprehensive bathymetry layer, so we use a different method of estimation based on the average distance from the shoreline to the 1 meter depth contour, which we multiplied by the length of the shoreline, which my graduate student painstakingly traced, and we got our estimate of habitable area that way. Next one, click more. Because there's some uncertainty in this, we also kind of fudged our upper and lower estimates as 50% and 150% of our centered estimate for the habitat area. Next slide, please. For the deposition rates of carbon, nitrogen, and phosphorus, it wasn't feasible for us to measure those ourselves for this study, although that's something I think would be really valuable to do in the future. So we relied on literature values for that. So we sort of searched the literature for SAV systems. What are the rates of deposition of carbon, nitrogen, and phosphorus? And from the literature, we got our sort of low end centered estimate and high end values. Next slide, please. Right, and so there was sort of a range of values for each parameter and slightly different sources for the carbon deposition rates, the nitrogen deposition rates, and the phosphorus deposition rates. Next slide, please. And so then we had to do our math. Fortunately, it was nothing more than multiplication and division. So I was able to do it. So we started with taking chute density, multiplying it by a biomass per chute, and that would give us sort of the biomass on a per meter squared area of the plant. We could multiply that by the percent carbon in the plant to get to the carbon per meter squared, and then multiply that by the habitat area to get the total carbon in the Caloosahatchee Estuary. For the nitrogen phosphorus, there was an additional step where you would have to divide by the C to N ratio or divide by the N to P ratio to get the nitrogen or phosphorus amount, respectively, for the estuary. And then the result of all that multiplication and division would be the total storage of C, N, or P in the Vallisneria tissues in the estuary. Next slide. There was a similar kind of flow of calculations for the sediment storage deposition. It's just that we would start with the literature values for deposition rates, multiply that by the estimated habitat area. And the fancy thing that we did in these estimates was we tried to account for the fact that deposition rates have been shown, one click please, in the literature to be proportional to the density of the SAV. So in a dense SAV habitat, you have larger rates of deposition of carbon, nitrogen, and phosphorus than in the sparse SAV habitat. So we sort of attenuated our deposition rate estimates by the fraction of full vegetation cover that you had in that particular scenario. So basically in the full restoration scenario, we assume the full deposition rates, but in the current scenario, we had a reduced estimate of deposition rates based on the relatively lower density of the plants. Next slide. And these are our results. I plotted the results on a logarithmic y-axis so that it would be easier to show all the results on one slide. And as you probably all know, on a logarithmic axis, between every tick on the axis, you're actually increasing tenfold. So a little difference in the height of the bars actually means about a 10 times difference. And so I want to kind of one pattern at a time show the patterns, talk about the patterns that are shown in the results of our model. One of the patterns is something that we probably could have predicted, right? And that's that there's more carbon in plants than there is nitrogen, and there's more nitrogen in plants than there is phosphorus. And there's about a tenfold difference. There's about 10 times as much carbon in plants as there is nitrogen, and about 10 times as much nitrogen in plants as there is phosphorus. So in these bars, there's 6 sets of bars here, and it goes carbon, nitrogen, phosphorus, carbon, nitrogen, phosphorus. This is the current scenario, and this is the restoration scenario. So besides the fact that there's more carbon than there is nitrogen, than there is phosphorus, you can also see that more is stored in the restoration scenario than in the current scenario. And this is quite a difference. It's more than a 2 order of magnitude difference in the estimated carbon storage between now and the potential future restoration scenario that we had. Another reason that I showed this on a logarithmic axis is that if this is not on a logarithmic axis, you can't even see the amounts that are being stored in the current abundance in the system. So basically, there's a paltry, minuscule, you could fit it in your pocket amount of nutrients that are being stored in the puny grass that's in the estuary now. But if we restored it, that would be orders of magnitude more and might become an appreciable fraction compared to our loading rates of nitrogen in the system. The other thing that I wanted to say about this slide is that the amount of these quantitative pollutants, carbon, nitrogen, and phosphorus that's stored at any one time in the biomass of the plants is a lot less than the rates than the amounts that are being deposited into the sediment. And there's a lot of sort of what ifs and caveats about this because we don't know if all of the material that's deposited into the sediment stays there, but potentially the amount that's being stored in the sediment exceed the amount that's in the living tissues at any one period of time. So that's even magnitudes higher than the amount that's stored in the tissue at any one time. Okay, next slide, please. So we're going to kind of go through the conclusions. Not sure how I'm doing at the time, but we'll do the conclusions one click at a time. So the first conclusion is that not much for nitrogen or phosphorus is being stored in Caloosahatchee Vallisneria in its current sorry state. Because these storage rates are proportional to the amount of plant, and there's not much plant, there's not much storage. Next slide. But orders of magnitude more could be stored if we could just rewind time to the 1990s. The storage would be better and the music would be better, everything like that, right? Next slide. Storage, the other insight is that storage by sediment deposition may far exceed tissue nutrient storage. But I have the ... because this is a part of the model where we use literature values, and actually making those measurements would give us more confidence in that part of the model. Well, this is manuscript is in its second round of review now, so we'll see. Hopefully, we expressed our uncertainty enough to satisfy the reviewers and get it published, so y'all can cite it. Next, but. The other thing I should mention is that nitrogen removal through denitrification could also be significant, but that's another one of those things that we haven't measured yet that we should measure. Next. And another caveat is that for this sort of sediment deposition storage to mean anything, it has to be long lasting, right? So if carbon, nitrogen, and phosphorus is stored in the sediments, but then the seagrass bed dies and it all washes away, then you're back to square one. So you kind of have to assume that there's this sort of long-term stability of these habitats for these storage estimates to be really meaningful. One more click. Another thing I want to say is that Vallisneria is not the only living thing in the watershed of the Caloosahatchee that might be sequestering carbon, nitrogen, and phosphorus. It's a big estuary, an even bigger watershed, and there are a lot of organisms and habitats in there that might have these beneficial ecosystem functions of sequestering carbon, nitrogen, and phosphorus, and we should consider some of those others. One more. One of the things in the current state of the Caloosahatchee, there's actually more seaweed in it than there is seagrass. And in the upper estuary, there's far more macroalgae. It's this low salinity tolerant red algae Polycyphonia subsolissima, which is really abundant up there and actually outweighs the Vallisneria. That would probably not be the case if we restored the Vallisneria, but right now there's probably more carbon stored in this macroalgae than there is in the Vallisneria. One click more. This also shows in a graph here, the green bars are the current biomass, the current percent cover of Vallisneria in the upper estuary, and the orange bars are the current percent cover at various depths of macroalgae. So right now we've just got this few slivers of green poking out from the mat of macroalgae. So that's a thing. And I believe I'm at the end here and I've got time for questions. I should acknowledge my funding sources, the CHNEP. Thank you for having me at the US EPA, which funded the shoreline survey of SAV abundance. Used data from the South Florida Water Management District and lots of published studies for this. And my co-authors, my former graduate student, Bronham Krebs, who's a PhD student at Louisiana State University now, who's studying the flower garden banks, beautiful coral reefs in the Gulf of Mexico, and started in our own Caloosahatchee Estuary, and Nicole and Jennifer, who are my co-authors on the study. So thank you, and I'll take questions.
Right.
Yes.
I was just wondering, did you consider taking dissolved oxygen measurements to compare how it tracked with the nutrient uptake?
I didn't think of that, but that's a great idea. Oxygen, providing oxygen is one of the most important benefits of plants. And I think that's something that people can relate to. And they know that we breathe oxygen, fish breathe oxygen. Sort of maybe quantifying the oxygen production of restoring these habitats, a cool thing to do.
So maybe you covered this and I missed it, but I'm just curious. Were you able to have any reference site where you could actually test the sediment to see what the carbon content and the CN ratio was to determine if it had the kind of carbon that the literature value has and if you're getting denitrification?
We didn't have Caloosahatchee specific data for that, right? So we just used literature values from other estuarine, marine, and freshwater systems. So that would be like a very obvious next step for us to do. Would be.
Are there areas you think where you could sample the soil?
Well, I think so. I mean, I might need a permit, depending on where I was taking dirt and how much I was taking. But you mean like an area that has dense vegetation? That would be tough to find in the Caloosahatchee, in the tidal Caloosahatchee now. But there are other West Florida estuarine systems that have a lot of Vallisneria in them, like up around Homosassa and Crystal River. There have been some successful restoration projects that have brought a lot of Vallisneria thick beds back into the oligohaline estuaries there. And we could sort of look at the sediments in those areas in comparison with the less vegetated sediments at Caloosahatchee, and that would be neat to do. Yes.
So in the Winter Haven area, we have quite a few freshwater lakes in our area. One of these, a lot of your work here really draws really good parallels between nutrient budgeting and the amount of SAV we have in our lakes. I know organizations like DEP have stipulated that like the removal of invasive aquatic weeds like hydrilla through mechanical means or the removal of things like tussocks come with some form of nutrient reduction benefit. Yeah. I'm wondering if this sort of methodology could be adapted to, calculate essentially the nutrient removal of some of these methods. Obviously, there's a lot of caveats associated with that. And my second question is, do you know of any other researchers that are looking into those sorts of practical applications of this type of work?
So yes, to the first question, I think it would be really neat to see what the potential crossover is between methods that are used for nutrient budgeting for sort of freshwater phytoremediation systems where you're using the aquatic plants and harvesting them to purify the water and this kind of system. I don't think we would want to harvest in the tidal Caloosahatchee Estuary because we're so focused on restoring the habitat. But a lot of the sort of math and techniques and things would be the same. So if you've got some references, send them my way. I want to see what people are doing in the fresh water. The other thing that's kind of an interesting well, you sort of pointed it out, but it's kind of an interesting irony is we're trying so hard to get this plant to grow in the estuaries now, but it's growing unbidden even in our ponds and canals and everything. In some places we're even poisoning it. So it's a little strange that we're, bending over backwards to try to fix the downstream end of the system while, we're treating the same plant as a weed even in other parts of the system, even though it's probably providing at least the same carbon, nitrogen, and phosphorus sequestration benefits in the other parts of the system. So maybe that's low-hanging fruit for where we could achieve a lot of carbon, nitrogen, phosphorus sequestration is developing more of an appreciation or quantification of those nutrient storage values that we're getting from Vallisneria and other freshwater aquatic plants in the watershed.
Gee, thanks for responding to that question real quick. Yeah, Martin County, Nick Lucia worked for Martin County and did an experiment on this and looked at nitrogen and phosphorus uptake. But he also looked at fecal coliform reductions and it's been accepted. Flexible aquatic vegetation has been accepted as a BMP, but additional research is needed to quantify stormwater benefits for municipalities. And in fact, now a company has hired Nick Lucia away from Martin County to work specifically on this issue for a statewide stormwater credit for municipalities, because that's really what's needed. It gets back to the why are we poisoning it and should we cultivate it and harvesting it, if anything, or remove it.
Yeah.
James, a quick question for you. Did you find Cara as a macroalgae? Because occasionally during the Angler Action study that we previously did, we would come across massive clumps of Cara on top of our grass beds that we had planted. But then they would disappear a couple months later.
Yeah.
We would have the other species that you showed.
Well, we must have been monitoring it during those times that it disappeared because I didn't see any. There were.
Go ahead, Kate.
Mhm.
Sorry.
I was wondering if you came across or have intentions of performing, is there any sort of like interest in looking at sediment, like denitrification, flux and content where there isn't vegetation? I mean, like I'm thinking about like a lot about like our canals and our navigation.
Right. Well, particularly in sort of like a still water system, there can be a lot of sediment sequestration of carbon, nitrogen, phosphorus, even without vegetation. And that's another part of the math that's kind of weak in my modeling approach, is that I don't have that as a null condition. They're sort of assuming that basically if there's no vegetation, there's no sequestration is not really a fair assumption. But given the water movements in the system, both tidally and from river flow, I think there is probably in bare sediment habitats in this system probably don't sequester as much as they would in like a still lake or pond. But that would something that we should check and not just assume.
I know there's probably a lot of factors at play, but what do you think is the biggest factor that's preventing the recovery of Cape grass in the Caloosahatchee River, or if there's kind of like a couple big factors in your opinion?
That's a super good question, because we kind of scratched our heads about that. So we know it's not just salinity, because we've done pretty well with salinity since 2011 or so, and it just hadn't really come back by itself. So we know that it's something else. And the two likeliest suspects are optical water quality and herbivores. We're not gonna, some of the herbivore question is tricky because there's a bunch of different herbivores, including both native and non-native species, like non-native apple snails and non-native herbivorous cichlids and things like that that munch the grass. But there's also really important native grazers like manatees. And so that's the grazers one is sticky. The optical water quality question aspect, one sort of indirect form of evidence that optical water quality is limiting the recovery is how much faster recovery has been in the spring-fed estuaries to our north, like Homosassa and Crystal River, where they lost Vallisneria for various reasons in those estuaries, and the same kind of paging restorations seem to be a little more effective up there. So the optical water quality might play a role. The estuary, the Caloosahatchee Estuary is sort of tannic, and that's sort of natural, but it's also to some extent a product of our water flow. It's like it's getting more quick runoff across the surface of the land, which is high in tannins, versus when water soaking into the groundwater or staying on the land for a long time before it runs into the water, then it lower concentration of tannins. So I think that tannins are it's a natural, that could be considered one of those quantitative pollutants, right? It's something that's natural, but the amount is not totally natural, right? So that could be part of our problem is light limitation. There also might be some changes in sediment conditions that are a limiting factor, and herbivory, and probably the multiple stressor effect of all of those things together is hurting it.
Okay, we want one more question.
Real quick, Dr.
Yes.
Douglas, you just alluded to this. I was going to ask about Crystal River SAV restoration with Vallisneria americana. About 63 acres have been restored since 2016. But then I understand just recently, because of Tropical Storm Idalia, there was this huge inundation of salt water. And as far as I know, a majority of the above ground biomass on the Vallisneria just dropped off. Do you think that's sustainable in the long term, or you know, I'm assuming the salinity event that was there from the Gulf into Kings Bay and Crystal River was relatively short term compared to Crystal River, but sorry, compared to Caloosahatchee River. Would you speculate that that could be a long-term event that would lead to kind of the loss of grasses there also? Say 72 hours as compared to pre-1999 conditions.
I want to defer that one to David Seeley, who's
We've worked on both projects right now.
Okay.
Kings Bay project.
Yeah.
They had a similar event happen in Michael, where the salt wedge came out into the system, and what they saw a die off of grass in the deeper areas, which you wouldn't expect because the salt water stays near the bottom, but it recovered. In fact, we're going to be doing reassessments of all these areas 1 year, 3 years, 5 years after restoration. There are several phases. We're in phase 5 right now.
Right.
We're going to do a post restoration phase 5 assessment here in the next month or so. Getting back to the herbivory and the water quality, I think James did a great job of explaining that. What I can tell you right now, if I took you out in the river, I could show you an area that we had about an acre of Vallisneria outside the cages. But after Ian, there's 2 cages out there that are full of grass, topped out, and there's nothing outside the cages. And then on the north side of the river, about 60% of the cages, they have 50 cages up there. 2/3 of them still have grass in them. But what happened was something about that event. There was a layer of silt, and there may be a shearing effect from the wave action or the depth of the increase. But yes.
Sorry.
2000.
Yeah,
Sorry.
yeah,
about
we had someone join and we had to mute them, so.
So another study we did in 2012, which led to a thesis at FGCU. We literally took the cages. And I came back the next day, the blades that were 3 feet long were grazed out to nose. It was still there.
Right.
But then a couple of weeks later, it was gone. So I like to say the salad bar was empty for so many years.
Yeah.
And when you loaded it up, the herbivores just came out. And so that's a big stressor. But water clarity is really important too. So it only grows to a certain depth of about 3, maybe a meter deep in the river because of the light attenuation.
Thank you, Dave.